I want to talk about a theorem that I think is really great because it helps really establish what a connected graph is, and I feel like sometimes establishing what a connected graph may be lost, and maybe that's more earlier stages of introduction to graph theory. But this theorem, once you have established what spanning trees are, this theorem allows you to have a way to establish a connected graph. And so the theorem says a graph is connected if and only if it has a spanning tree. So this is a biconditional statement. If and only if means we can read it forward or backward because the converse is true. So the first piece we're going to do is we're going to prove that if a graph is connected, then it has a spanning tree, and then you have to turn around and reverse that and prove that as well to prove the entire context of the theorem. So I have a little diagram over here to the side to kind of help us think through some of the process of establishing this part of the theorem. So if we take any graph with the assumption that is connected, we want to create subgraph T from graph G, which is, I'm labeling this my graph G. And to create the subgraph, we are going to remove edges from it to create a spanning tree. Now, a little recall, there's a theorem that says that in a tree, there is a unique simple path between each pair of vertices. So that is another important concept that we need to have to help firmly establish this theorem. So given any graph, we should be able to remove some edges, but maintain all the vertices so that the subgraph T is going to have all the original vertices of the main graph, but have less edges. And we are removing edges to create a tree. So our objective is to eliminate the circuits that are present in the graph. If there are no circuits, then great, we already have a tree and we are done. And so we've established a spanning tree there, and we know that there is a unique simple path between each of those vertices, and therefore it has to be connected. All the vertices are incident with an edge that allows you to travel through that graph. So we are not going to start with something that's already a tree. That's trivial. So when I look at this, I'm going to have to go through some process of thinking. You may or may not have an algorithm for doing this at this point, but we're going to go through here and break circuits. And so right here, I see this triangle here. I know there's a circuit there. So what can I do to break that circuit? Well, one thing I might do is I might eliminate this. As I look at this, I also see this quadrilateral over here that's going to cause me to have possibly a circuit as well. So right away, I'm going to eliminate that. Okay, so maybe I want to look at coming in from the right-hand side here because this kind of has this tail end. I can see that tree sprouting from there. So as I come here, I go this direction, I go this direction. I'm going to need this. I can come down here and maybe eliminate this. So now I have something that looks like this, 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 this. Alright, so there's my tree. I have a spanning tree here. These spanning trees are not unique. You can come up with your own from the graph. So now I've created this spanning tree. So I've demonstrated that we can create spanning trees by removing edges. And this theorem here tells us that we will have a unique simple path between all the vertices. So we've shown that if we start with a connected graph, we can create a spanning tree through this process. You may be able to set up an algorithm, or if you've already been shown an algorithm or you've learned about an algorithm, you can use that algorithm for establishing your spanning tree. So that's the first part. So then the second part is you have to go the other direction. Assume that you have a spanning tree, then show that your graph is connected. We are going to look at going the other direction now. We're going to prove if a graph has a spanning tree, then the graph is connected. So we get to assume that T is a spanning tree, and we also get that T is a subgraph of G. So we want to show that since T is contained in G, then G is in fact connected. So since T is in G, T contains all the vertices of G. So that's an observation that you could make. So the set of vertices in T is equal to the set of vertices in G. All right? So it contains all the same vertices. Now the edges can be different. That's allowable because in a spanning tree, just like how we did the first part of the argument, we are allowed to remove edges to create the spanning tree from the original graph. So now we're kind of going the other way. Can we take a spanning tree and build another graph from that? That's kind of the idea that we're going for. So we've made this observation. All the vertices are going to stay the same. We know that this theorem is also going to still hold because it affects directly the subgraph T. T is a tree. There's a unique simple path between any two pair of vertices. Since both graphs contain the same vertices, we know that in this one specifically, all the vertices have a simple path connecting them. Our reason is because of this theorem here. All right, so everything in T is connected because we have any pair of vertices has an edge incident to them. All right, so a definition of the simple graph. So that's by definition. All right, so T is a simple graph contained in G. All the vertices are the same in T and G, and there is a path between all the vertices. Since there's a path between every vertice in T, which is also every vertice in G, that means there is a simple path in G. So since there are paths between vertices in T, and T is a subgraph of G, then there are paths between vertices in G. And at this point we have what we wanted. We've shown that G is connected. In this case, the G is our second piece to this. We start with T, we end with G, because we're building from a spanning tree into any connected graph. So therefore, G is connected. All right. So we've shown this both ways, and with this demonstration, each side of it we did a little bit of a different proof. I kind of talked you through kind of maybe an algorithmic way to do the first part of this, and then we've done this with some justification and writing it out. So hopefully if you need this for some specific example, you can put this together and get the kind of ideas that you need out of it to be able to present. Cheerful calculations.